So now we can derive an evolution equation for u. So if I take u and take its derivative, so I have t of u, del u by del t, so t by t naught. So if I look at the expression for u, the expression for u is this, or let me just write it again over here. U t comma t0 is e to the power I h naught t minus t0 times e to the power minus I h t minus t0. So if I take the derivative of this, so what will I get? I'll get two terms. The first term will be the derivative of this thing, and from there I will get I times e to the power I h naught t minus t0 times h naught. So I h naught comes down, and then we'll have e to the power minus I h t minus t0. And then I will get another term which is minus I e to the power I h naught t minus t0 times h, and then e to the power minus I h t minus t0. So now note that this factor and this factor is the same, and this factor and this factor is the same. And I is the same here, and there's a minus sign relative in the two terms. And noting that the total Hamiltonian H is H0 plus H interaction, we can write this as del U by del T. U depends on T and T naught. This is going to be given by minus I e to the power I h naught t minus t0 h int e to the power minus I h t minus t0. So then what we can do is that we can rewrite this. We can rewrite the right-hand side. We can introduce the first two terms, remain the same. But what we can do is that minus I can be moved over to the other side, so this becomes a plus I. And then I have e to the power I h naught t minus t0 h int e to the power minus I h naught t minus t0. So this is a new factor, so to cancel it, I have to insert e to the power plus I h naught t minus t0, and I have e to the power minus I h t minus t0. Now, if I look at this thing, this h int is the interaction Hamiltonian in the Schrodinger picture, and therefore, and these guys basically just transform it to the interaction Hamiltonian in the interaction picture. So we can write this as h interaction in the interaction picture, and this will depend on time in general. Why would it depend on time? Well, that's because we are making the unitary transformation with respect to h0, but here we have h int. Since h0 and h int are not the same Hamiltonian, they will not commute in general, and therefore this guy will not go through and cancel this. So, and therefore the whole thing will be in general time dependent. And what about these two guys? These two guys, if you go and look here, this is nothing but the unitary operator that transforms us from the Heisenberg to the interaction picture. So this is going to be u of t comma t0. So this is what we called a Schrodinger-like equation. And this is the evolution equation for the states in the interaction picture. So, here we are just writing it in terms of we are just right in terms of the time evolution operator, but of course we can apply it to some state, say psi at time 0. If you apply this equation to the state, what we get is that I del of psi d by dt of psi as a function of t is equal to h int of I times t acting on psi at t equals psi t. So differential equations, of course, need to be solved with a boundary condition. So the boundary condition for this differential equation is going to be u of t, or t0, t0 will be just 1, which translates in this case to psi of t0 is, of course, just itself. So what we found is that we found for the state a Schrodinger-like equation. So this is not exactly the Schrodinger equation, because Schrodinger equation has here the total Hamiltonian, but here we have the interaction Hamiltonian in the interaction picture. So we can also derive an equation for the field operators in the interaction picture. Remember that the field operators in the interaction picture are given by this transformation from the Schrodinger picture. And now, in a very simple exercise, one can show that the time derivative of the interaction picture field operator is given by the I times the commutator of H0. Oh, sorry, there should be an H0 here and H0 here. The commutator of with H0 and phi I of x. So this is remarkable because if you look at this equation, although we are looking at the evolution of an operator in an interacting field theory, the evolution of that operator is given by the Hamiltonian of the free theory, and therefore, if we can, which is something we noticed before, if we write phi of I of x at some given time, t of so at some given time, which is something like this. Because the equation, the Heisenberg-like equation of motion satisfied by phi I is the free version of the equations of motion, we see that the field will have this nice form for all time. So what's happening? What is happening is that when we go to the interaction picture, both our state and our operator depend on time, unlike in the Heisenberg picture and the Schrodinger picture, but they're both given by an equations which are relatively simple. It's especially simple for the operators, which is given by the free version of the operator equations, but the equation for the state is given by a Schrodinger-like equation,